Hello everyone, and welcome to another seminar at Physics Latam. Today we have the third lecture by Yukinobu Toda on moduli spaces of semistable sheaves. Please go ahead.
Okay, yeah, thank you very much. So today I give some introduction about moduli spaces of semi-stable sheaves. So that is quite important theory in Donut theory and Gopakumar-Vafa invariants. And this is also important in classical algebraic geometry because this gives a source of several interesting geometry. And also this is also interesting in like geometric representation theory. So first, let me give some brief idea what is the moduli space. So basically, you want to count some geometric objects like curves or points inside some space. But so if this is the only finite number of points, if this is finite set, then we can just count the number of such objects. But usually such geometric objects form some family. And in that case, we have some interesting geometry of set of such geometric object. So in general, let there be some set of geometric objects we want to consider. For example, for given variety X, we consider the set of all the curves or the set of some point in a given space. For example, right, also we can also consider the set of surfaces, so a set of some vector bundles. And in some cases, so that there is some nice geometric structure. So the meaning of this geometric structure varies in the context, and sometimes it is algebraic variety or scheme, but sometimes we put some more interesting and deeper structure, like a stack or a derived stack. And it depends on the context, how much information you want to get from this space. But anyway, so in general, we call such a geometric space as a moduli space. So here is a very simple example. So let M be the set of all the lines in PP2. So P2 is a two-dimensional projective space. So let's consider a line inside P2. So if we take the homogeneous coordinate of P2 as y0, y1, y2, then every line inside P2 is written in this way. So for some choice of y0, y1, y2, so this is given by this linear equation. So giving such a line is equivalent to giving the tuple of this numbers in C3, these pairs in C3. And but of course you have to eliminate 0, otherwise this is just fits itself. So then also we have that these two lines are same if and only if these vectors are proportional. So in this way, if we consider the set of all such lines, then this is parameterized by a point in C3 minus 0, but we take a quotient by C3 which identifies these two lines. So as I said, we get this PP2. That is, every point of this line has a one-to-one correspondence in P2. And of course, P2 has a geometric structure. That, of course, this is algebraic variety. So in this way, we can say that this P2 is again the moduli space of lines in P2. In fact, this is like real projective space. And as I said, so that this moduli space is very important notion in mathematics, not only in algebraic geometry. I will also see later that so they also provide important classes of algebraic varieties. For example, if we consider moduli space of some sheaves on KC surface, then it has a holomorphic symplectic structure. This is a very interesting example of holomorphic symplectic algebraic varieties. Also, as against enumerative geometry, we want to consider enumerative invariants of curves. And we want to consider moduli space of curves inside some varieties. And they are defined as moduli spaces of some kind of curves on a given space. So it also depends on the context, what kind of curve we should consider. And depending on the context, you have different moduli spaces. And as I said, so this is also important in representation theory. So if we have the moduli space, then we can consider some cohomology theory of that moduli space. And in many cases, it provides many interesting representations of some important groups like quantum groups. So the moduli space is interesting not only in algebraic geometry, but also in several branches of mathematics. However, for example, in the case of lines in P2, I said that the moduli space is again P2, but there are some ambiguity of the notion of moduli space. So usually when people say moduli space, so we have some space M, so that each point corresponds to some geometric object. For example, at each point you may have some curves, say C1, say C2, or so on. But if you can find such a space, it is not clear what kind of geometric structure you should consider. For example, in the case of moduli space of lines in P2, of course, it has a natural algebraic geometric structure, but we can also consider other geometric structures, like, for example, this may be disjoint union of C2 and also P1. As I said, so this is also identified with P2. And also, we can also even consider the P2 as a discrete set of points, just parameterized by a point in P2. So a priori, if you just say moduli space as some space whose point have close one-to-one correspondence with the geometric object which we want to consider, then there are some ambiguities about its structures, geometric structures. However, this issue is solved if we consider the functor associated with moduli theory. That is, so not only consider some space which has some one-to-one correspondence with the geometric object, we also consider some families of such geometric objects, and that forms some functor from the category of schemes to some set. So then we consider some space which represents such a functor. So the key point of this idea is that so the scheme itself is regarded as a functor. That is, there is some free face functor from the category of schemes to the category of functors from the opposite category of schemes to set. So this is a category of functors that whose objects consists of functors from this category to this category. And this embedding is given by sending each scheme to this functor. That is, for each scheme Y, we associate this set of maps from Y to X. So then it is each exercise that this is in fact a free face functor, and we can regard the scheme as a functor. So then from this point of view, when considering moduli space, we usually consider a functor from the opposite category of the category of schemes to the category of sets associated with the moduli theory in question. So usually we want to take MS to be the set of families of geometric objects which we want to consider, and so this is the family of objects parameterized by S. For example, if we want to consider moduli space of curves, then we want to take MS to be the set of families parameterized by AS. So then we say that this moduli, we say that M is represented by a scheme M if this functor is isomorphic to the one which is coming from the Yoneda embedding. That is, as I said, so there is a free face functor, scheme of C to functor. So if given some moduli functor, if it is coming from this image, then we say that the one coming from here is a moduli space. And in fact, so this is the moduli space in the strongest term. So we say it is a fine moduli space. And moreover, because the Yoneda embedding is free face, this moduli space M is unique up to isomorphism if it exists. So this means that if the functor is represented by a scheme, then there is no ambiguity of the geometric structures on it. For example, in the case of moduli of lines in P2, we consider this functor, that is, for each scheme S, we consider the flat family of lines over S. So this is a closed subscheme over S product P2 that is flat over this factor S. So then this functor itself is represented by P2, not like the disjoint union of sheets and P1, or not the discrete point of not the discrete point. So in this case, so that there is a unique geometric structure on this moduli space. And there are also several other advantages of considering the moduli space as a functor. So the first of all, if the moduli functor itself, the moduli functor is representable. So then, by the definition, there is some tautological element. So this means that M is what the HM is a functor from to M. So this means that the if this moduli functor itself, moduli functor is isomorphic to this representable functor, then there is this element corresponding to the identity element. So this element is some sort of family parameterized over this moduli space. And this element is called a universal family. That is, for each point in M, its restriction to that point is the one which corresponding to that point. That is, for each x in M, if you take U over X. So then this one is the corresponding object X. Another point is that we can also consider not only a point, but over some point over the spectrum of the Artinian link. So this is the good point of considering the scheme theory, that, for example, we can talk about the spectrum of some Artinian link, which was not possible for just usual varieties. So we can consider this M spec R, and this is the family of objects parameterized by spectrum over Artinian link. And this one corresponds to certain infinitesimal deformations of the object, which we want to consider. For example, if we consider M spec CT over T square. So this object corresponds to that. If you restrict it to spec of just C, so there is a closed embedding from here to spec of CT over T square. And if you restrict it to here, then it corresponds to some object, and the set of this the set of the image of this functor corresponds to the deformation of E to the spectrum of CT over T square, and that corresponds. This space is nothing but the tangential space of this moduli space at E. So this is identified with Tm at this point E. Now I give some more classical examples. For a smooth projective curve of genus G, let JC be the functor which sends scheme over C, the opposite category of the category of schemes to the category of sets, which sends each scheme S to the some equivalence classes of line bundles over C product S. So this is regarded as some family of line bundles on C parameterized by S, such that we also assume that each restriction to each point in S is of degree 0. So this is a numerical condition of each line bundles. And for some reason, so I will explain later that I have to put this equivalence relation that everyone and its are equivalent if L1 and it's isomorphic up to some tensor line bundle over the base of the family. So then this factor is known to be representable, and the scheme which represents this factor is called Jacobian of the curve C. In fact, this is explicitly described as this complex torus. So this is because this is also classical fact that you consider H2 C or C star. So this is nothing but the space of line bundles over C. And I'm taking the condition that this is of degree 0. So this means that there is a map from here to here that corresponds to the first chunkus. But there is a long exact sequence associated with this exact sequence of sheaves. And so the kernel of this one is in fact comes from so this is H1 OC and H1 of CD. So the set of line bundles of degree 1 is in fact the kernel of C1. But the kernel of C1 is from this exact sequence given by the cokernel of this map. So the cokernel of this map is nothing but this quotient. So this is in fact a complex torus. And when the G is 1, then H1 OC is just one-dimensional, and the Jacobian is isomorphic to the original elliptic curve itself. In general, this is a G-dimensional complex torus, which is known to be algebraic variety. So this is a modular space of degree 0 line bundles on this curve C. Here is another example. So this is a Hilbert scheme of points. For a precise projective scheme and non-negative integer n, so let Hilbert x to be the functor which sends the scheme over C to the category of set, which sends each scheme S to the flat family of zero-dimensional subschemes on family of zero-dimensional subschemes parameterized by S. So this is a S-flat closed subscheme such that for each restriction, this is zero-dimensional such that the chi OS D equals N. So this condition means that so generically this means like a set of so this is something like the closed subscheme corresponding to the endpoint. So we have this space. So for example, we have this, let's say for example, for simplicity n equals 2. So then generically you might have this two points. But at some special point with, for example, it moves to some point and it may correspond to some fat point. For example, like the image of the map from a spectrum of CT over T square to X. So this is not only the zero cycle on this X, but there are also some something like that the information of the tangent space. And in fact, so this is known to be a precise projective scheme, and this is called Hilbert scheme of points. So this is the modular space of zero-dimensional subschemes, see, and whose Euler characteristic equals to n. So there is a natural map from Hilbert scheme of points to the symmetric product of x. So this is quotient of x to x n times, and then take the quotient by Sn, so by the permutations. So this map is just sending each closed zero-dimensional closed subscheme to its support. But it forgets about the tangent direction. For example, in the case of n equals 2, we also have the information of how this point is patterned. In fact, when x is smooth, then this is nothing but the blowing up of when x is smooth and n equals 2, then this map is nothing but the blowing up at the diagonal. And when x is one-dimensional, this is isomerism. But when n is bigger than or equal to 2, and dimension x is also bigger than or equal to 2, then this is not isomorphism. So there are some non-trivial fibers. Well, then we are interested in moduli spaces of coherent sheaves. So we want to consider some flat family of coherent sheaves. So for simplicity, let's assume that X is a smooth projective scheme. And let's take V in the cohomology, usual singular cohomology group of X. So then it is natural to consider the functor like this. So V is just the numerical class. I want to fix some Chan character of the sheaf F, which we want to consider because the Chan character is, in fact, locally constant along the flat deformation of the coherent sheaves. So it is natural to fix that Chan character. For example, in the case of curves, this is corresponding to fixing a rank and degree of coherent sheaves. So then we can consider this functor, which sends each C scheme S to the equivalence classes of sheaves. So this equivalence class is the similar one which I discussed in the Jacobian case. So I take equivalence distribution coming from the pullback of line boundaries over the base. So then this functor is given by sending each scheme to the equivalence classes of flat families of coherent sheaves over S, such that its Chan character equals to given V. So this is very natural to consider. However, so this functor is not represented by a reasonably nice scheme in general. And in fact, there are at least two issues. The first issue is about the existence of automorphisms. So in general, if you consider some modular theory so that each object has some sort of non-trivial automorphisms, then usually the modular functor is not representable. And I will explain later that usually you have to consider modular stack in that case. Another issue is that so there is some unboundedness. So ignoring the first issue, we may still able to get some modular space, but it does not have some finiteness property because even if this condition is fixed, there are so many types of coherent sheaves, and in fact there is no nice finite type modular space which represents such a modular functor. So let me explain the first issue first. So for simplicity, let's consider the case X is just a point. So in this case, of course, the category of coherent sheaves over the point. So this is equivalent to the category of finite dimensional vector space. So this is nothing but considering the modular space of the vector spaces. So in this case, the functor which was considered in the previous slide is given this way. So this functor is given by sending each scheme S to the, of course, this is X is a point, so we consider flat family of coherent sheaves over its product of a point. But the flatness over S is nothing but the sheaf is just locally free or vector boundaries. So this is a functor in the case of point, in the case that X is a point, that for each S, scheme S, we consider the set of vector boundaries over S. However, it cannot be represented by a scheme. This is because if there is a scheme M which represents this functor, so then by the definition of the moduli functor, each closed point of that scheme M corresponds to rank curve vector bundle over the point. That is nothing but the rank curve vector R-dimensional vector space. But of course, there is only one unique R-dimensional vector space up to isomorphism. So if there is such a scheme M, then it must be trivial. So it must be just one point. However, this means that if this moduli functor is representable by a point, this means that every for each such vector boundary over S, there might be some map from S to point M, such that this functor must be a pullback from the family over M. So this means that every such vector bundle over S must be trivial. But of course, this is not true. So depending on the global geometry of S, there might be some non-trivial vector bundle. So this is caused by the fact that the optimism group of this R-dimensional vector space is non-trivial. So this is GLRC. So this is because if there are some non-trivial optimisms, so then we have the some transition functions of the vector bundles, which makes this vector bundle to be non-trivial. So in this way, if there are some non-trivial optimisms, then we have some non-trivial family over non-trivial base, which makes the moduli theory to be non-representable. So the second issue is unboundedness. So let's also this. So this unboundedness does not is not a problem in the case of x is a point, but there is a problem in the when x has a positive dimension. For example, let's consider x is just p1 and take v equal to 0. So this means that I'm taking v to be h0x plus h2x. So the Chan character v equal means that I consider rank 2 and degree 0 vector bundle on this curve x. So then the set of vector bundles on P1 is, as in the previous lecture, so the set of the vector bundle on P1 decomposes into the direct sum of line bundles. So the only set of vector bundles on P1 with this Chan character is classified in this way. So this is nothing but the direct sum of two line bundles, where the sum of each degree becomes just 0. So then we have this infinite number of such vector bundles. The point is that so we have infinite number of points, and each point degenerates to another point. That is. So for example, there is this exact sequence. So the map from OP1 plus 2 to OP1 is given by the homogeneous coordinate y0 and y1, and this map is given by y1 minus y0. So this means that this middle one, so this one is given by extensions of these two line bundles. So in fact, so this is a non-trivial extension. So this one corresponds to the in x1 or 1 or minus 1. So then if we take this extension class, for example, if we take some multiplication of t star and then take t to 0 limit, then we get the direct sum of OP1 minus 1 and OP1. That is nothing but F1 in this notation. So this means that the sheaf F0 degenerates to F1. And in a similar way, so the sheaf F1 also degenerates to F2. F0 degenerates to F1, F2, and so on. So this means that among these set of vector bundles, there is no closed point in the moduli space. At every point, if you take a closure, then you get another point. So in particular, it cannot be of finite type space. So in order to avoid these issues, we the traditional way to construct moduli space is to consider only some special type of coherent sheaves called semistable sheaves. So the notion of stability condition was introduced in order to obtain these nice moduli spaces. So I first explain in the case of curves. So for a smooth projective curve, C, and also and for each coherent sheaf, I define its slope to be the ratio of degree f and the rank of f. So the degree of f is, so this is the same as the first chunk class. And rank f is 0 or positive. And if the rank is positive, then this is well defined. And when rank f is 0, this means that f is just a Trojan sheaf. And in that case, I always set the slope to be infinite. So then the semi-stable sheaves or stable sheaves are defined so that for any non-trivial subsheaf, we have the inequality of slopes. So this condition automatically implies that f is either Trojan sheaf or Trojan free sheaf, because if f contains a Trojan sheaf, then because of the slope of the Trojan sheaf is infinite, then it violates the stability condition. So this happens when f is Trojan. For example, in the case of C equal P1, the every vector boundary decomposes into the direct sum of OP1A. And from this definition, every semistable C from P1 is just a direct sum of the line boundary of the same degree. So here are the examples of semistable sheaves. Now, of course, any line boundary on C is stable because for any if every is a line boundary, so then for each subsheaf, then this is also again line boundary. So the rank are the same, but the degree are decreasing. So it must be always stable. And for in the case that the curve is C1, as I said, this vector boundary is semi-stable if and only if it is a direct sum of the line boundary of the same degree. Because otherwise it decomposes into for example, if LP1, A1 plus R1 plus OP1, A2 plus R2. If A1 is bigger than A2, so then this part destabilizes such shifts. So if A1 is less than A2, so then this has the bigger slope, so it destabilizes this shift. And this is stable if and only if it is a line boundary. So in this way, in the case of P1, this avoids the unboundedness issue which was mentioned before, because in the case of rank 2 and degree 0, the only shift which need to consider is just F0. So F0 was OP1 plus 2, and this is the only semi-stable shift which appeared in the previous slide. Also, let's consider the case G, C is bigger than or equal to 1. Then for each point P in C, there is some non-trivial extension of this form. So if this splits, then this is not stable because if F splits, then OCP is a subsheaf of F, which violates the slope inequality. But if it does not split, then every subsheaf of this one has slope big less than or equal to 0. So this sheaf has a slope 1 over 2. So it must be stable. And so this condition is necessary because yes, for example, by using the Riemann-Roch theorem, this extension group that is OCP, OC. So this is H1 of OC minus P. So this is G-dimensional. So when G is positive, this is non-zero. So we can always find some non-trivial extension which gives a non-trivial example of stable vector bundle on curve. So the considering the semi-stable sheaf restricts to the considerations of semi-constellation of coherent sheaves. But in some sense, the semi-stable sheaves and stable sheaves form a building block of all the coherent sheaves. So this is given by so-called Harder-Nashman filtration and also Jordan-Helder filtration. For any coherent sheaf on C, so there is a filtration which is unique up to isomorphism. This is called Harder-Nashman filtration, so that each subquotient is in fact semi-stable, and there is an inequality of slopes like this. So this means that each subquotient is semi-stable, and we can recover the original coherent sheaf E as some successive extensions of the semi-stable sheaves. Furthermore, every semi-stable sheaf admits a filtration called Jordan-Helder filtration. So contrary to the Harder-Nashman filtration, this Jordan-Helder filtration is not necessarily unique. But nevertheless, so there is such a filtration so that each subquotient is stable, and now the slopes are the same. So this filtration is not necessarily unique, but it is possible to show that the associated gradient of this filtration is unique. That is the direct sum of Fi prime. So this is unique up to ISON. So in this way, the stable sheaves also form a building block of all the coherent sheaves. So then using the notion of stability condition, we can construct moduli space of stable sheaves or semi-stable sheaves. So this is a very classical one. And so for a smooth projective curve, let's take V. So this is a chunk character that is prime. So this condition implies that there is no strictly semi-stable sheaves of this chunk character. This is because if the sheaf is semi-stable but not stable, then the rank and degree is not coprime. So then in this case, the functor which sends each scheme S to the family of stable sheaves, also again by taking up to some equivalence classes. Then this is represented by a smooth projective scheme. In fact, so this is a smooth projective variety. And so this is quite classical object to study. And in fact, when R equals 1, then this is nothing but the Jacobian which I considered. But in higher rank case, this is much more interesting example of the moduli space. And this scheme is called moduli space of stable sheaves on C. So this is interesting even in the rank 2 case. In the genus 0 case, there's nothing, because in the genus 0 case, the moduli space of, because I assumed the rank and degree are coprime, then the moduli space becomes just empty. This follows from the classification of the vector bundles on P1. But for the genus equal 1 case, that is when C is empty curve. So then this moduli space of rank 2 and degree 1 is, so this is isomorphic to the original empty curve itself. So this isomorphism is also explicit. That is for each F. So this is a rank 2 and degree 1 a stable bundle. Then we can associate its determinant line bundle. So then it becomes the element of the Jacobian. But in the case of elliptic curves, Jacobian is also isomorphic to C itself. And also for each point of X, we can also consider this point. That is, we can construct rank 2 stable bundle just by considering these extensions. In the case of genus 1, this extension is unique up to isomorphism because x to 1 is only one dimensional. So in this way, we have this isomorphism. And for genus 2, so we can also consider the determinant map from this moduli space to the Jacobian. But in the genus 2, this is not isomorphism because it has bigger dimension. And in fact, this is a smooth map, and each fiber is isomorphic to the intersection of quadratic inside P5. So this has very interesting geometry. So that was the story in the curve case, and we can extend it to the higher dimensional case. But one difference in the higher dimensional case is that the stability condition is not canonically determined, and you have to give some choice. And classically, the choice of stability condition on the category of coefficient sheaves is given by a choice of some ample divisor h on x. So after choosing some ample divisor, well, we can also consider some ample divisor with Q coefficient or R coefficient. Anyway, so after taking point in the ample cone of x, and also by taking in coefficient shifts, we can redefine its behavior polynomial in this way. So by the Riemann theorem, this left-hand side is given by the chunk vector of E multiplied by exponential of mh, and so multiplied by tot x and its integration. And after expanding this exponential, this is given as a polynomial in M. In fact, this is a polynomial. So in the case of curves, so this is just a linear function that is, for example, when x is one-dimensional and E is torsion-free sheaf, then this is basically like a rank, and this is like first chunkers. And the slope is nothing but the ratio of each two coefficient. So similarly to the curve case, we take the ratio of this polynomial by the leading coefficient of this polynomial. So when E is torsion-free, the degree of this polynomial is the dimension of x. But in general, the degree of this polynomial is the dimension of the support of the sheaf E. The support is given by the set of points where the stroke of E is non-zero. So this is a closed subscheme, closed subset of X. So then we define the reduced Hilbert polynomial by taking the quotient of the Hilbert polynomial by the leading coefficient of this polynomial. So then we can define the semi-stable sheaves in general. Let's take for a smooth projective variety, let H be an ample divisor on it. So then a coherent sheaf E or X is called H semi-stable or H stable if first it is a pure sheaf. That is, there is no subsheaf where the dimension of the support is less than dimension of the support of E. In the case of curves, this corresponds to that E is either torsion sheaf or torsion-free sheaf. In the higher dimensional case, so we also have something similar condition. And then this corresponds to the inequality of the slopes, that for any non-trivial subsheaf, we have the inequality of the reduced Hilbert polynomials. And the order is that we have this inequality when M is sufficiently big. So it's because that this is reduced Hilbert polynomial. And similarly to the curve case, we have the notion of Harder-Nashman filtration and also Jordan-Hölder filtration for H semistability. So these semi-stable sheaves and stable sheaves form a building block of the category of coherent sheaves. However, the important difference from the one-dimensional case is that the notion of stability condition depends on a choice of ample divisor H. So if you change H, then the notion of semistability also changes. And it is very important to understand how these notions change under the change of ample divisor. Anyway, so we can similarly consider the moduli space in general case. So yes, for simplicity, let's assume X is most projectivity, but we can also remove this condition. Let's say like smooth, not say like projective scheme, and also take H to be ample divisor on it. And let's take V as the image of the Chan character map, so that corresponds to a choice of the topological data of the sheaf. So then, in the rank one, in the one-dimensional case, I assumed that the rank and degree are coprime. In the higher dimensional case, the corresponding condition is that the greatest common divisor of this Hilbert polynomial is equal to 1. And this corresponds to some sort of primitivity of this vector. So then the factor of families of H stable sheaves. So this is represented by a projective scheme. So, but contrary to the case of curves, in general, so this might be highly singular. In the case of curves, there is no singularity because I will also talk about deformations and obstructions, but in the case of curves, there is no obstructions because basically there is no x2 of each vector boundary. But in the higher dimensional case, there might be some x2 which obstruct the deformations of coherence sheaves, and the moduli space is usually singular. And this scheme is the moduli space of H stable sheaves. So here is a very important and famous example. So let S be a KC surface. So recall that this means that the canonical line bundle of S is trivial, and also H1 of S equals 0. For example, the one example is S is like a quadratic KC surface, quadratic hypersurface. Then if we consider this moduli space, which represents the moduli functor, so then this moduli space is known to be homomorphic symplectic manifold. So this was first proved by Mukai. In particular, if this is two-dimensional, then it is again a KC surface. So this is very important because it provides one very few example of compact homomorphic symplectic manifold. For example, if you take V to be like 1 something something, that is rank 1 case, then M is in fact isomorphic to the Hilbert scheme of point. And it gives the example of homomorphic symplectic manifold. And in general, it is known that such moduli space M is deformation equivalent to the Hilbert scheme of points. And the homomorphic simplex structure on this moduli space is given by a serial derivative pairing. That is, for each point of this moduli space. So this we can construct this homomorphic symplectic form from the serial derivative pairing. So I haven't explained yet, but the tangent space of the moduli space is canonically identified with the x1 of the sheaf. And we have the natural map. So this is just the coupled product. But by the serial duality, so the x2 is in fact identified with C. This is because the serial duality implies that this is isomorphic to form of EE and it's dual. But if E is stable, then it is shown to be one. The homo space is shown to be one-dimensional. So this is just one-dimensional. So I get this map, and it is shown to be perfect pairing. That was the two-dimensional case, and so we are most interested in the case of a three-dimensional case. So let's assume that x is dimension of x is 3, and also the canonical bundle of x is trivial, so x is Calabian threefold. And for some purpose of simplicity, I assume that the H1 of the structure sheaf is also 0. So then let's take V to be the of this cohomology class, where beta is a Poincare classable curve, Poincare dual of a classable curve. So a priori beta is the element BH to X, but by Poincare duality, I regard it as element in H form. And similarly, N is the element H. Similarly, H6X is one-dimensional. So I identify N as a class in H6X. So then the moduli space. So in this case, this is very special that the moduli space is independent of the choice of H. And in fact, the moduli space consists of ideal sheaves, where C is a closed subscheme, where the dimension of C is less than or equal to 1, whose homology class equals to beta, and its Fourier characteristic equals to n. So this moduli space is, so this is the Hilbert scheme of curves in X. And this is also denoted by this. And in fact, so this is independent of the choice of the ample divisor H. And this moduli space will be very important in Donaldson-Thomas theory. Another important moduli space is that this looks similar to the previous slide, but there are some crucial differences. Let's take x is three-dimensional and also kx equals 0, and also take v to be of this cohomology class. In the previous example, it was something like 1, 0, something, something. So it was rank 1. But now, so the first vector starts from 0. So this is, in fact, rank 0. In fact, this corresponds to some torsion sheaves on X. So the moduli space, the moduli space is getting in this way, and each point corresponds to a sheaf on X, whose support is one-dimensional. And the fundamental homology class equals to beta, and chi f equals 1. I will go back to this moduli space later, but one difference is that in the previous slide, I'm only consider some structure sheaf of some closed subscheme. For example, if you consider some curve in X, which have some higher rank on X. For example, if you have a curve C and also the vector bundle over this curve, then there is no surjection from OX to F. So in that case, there is no corresponding point in the Hilbert scheme of the curves. But in this moduli space of one-dimensional sheaves, we also consider something like a vector bundle supported on some curve. So in this way, the moduli space is in fact different from the previous one. So then again, yes, so this one, yes. So yeah, so this one, yeah, there is some factor about the genus. So chi or C is, for example, if C is a smooth curve, then this is 1 minus G. So the information of N is something similar to the genus of the curve. But here, so there are some more data which is involved. So if there's C, and there might be some point over here. For example, if we consider C prime to be C and also some zero-dimensional closed subscheme, there are also such a contribution in this moduli space. And so anyway, so in this case, so there are some, something information about the genus and also some information of the point of the closed subscheme. So on the other hand, so in this moduli space, so there is no information of the genus. There is only the homology class, and so in fact, only set chi. So this is the chi. So this one corresponds to this factor, and I'm taking chi f equal 1. So this means that this is something similar to fixing a genus if f is a structure C of something. But f is not a structure C of something. So f is something like a vector bundle on a curve. So you should not understand it as something like a genus. So in this moduli space, there are several curves with several genus appears in this moduli space. And the point of the Gopakumar-Vafa invariant is to pick up the fixed genus contribution from this moduli space. So does that answer your questions?
Yeah, so in this case, you are fixing it by 1.
Yeah, but that's right. But this is very important because so from physical point of view, there is no reason why we should take chi equal 1. And in fact, we can also consider this moduli space for other one. For example, we consider this one. So yes, so this is I'm taking, yeah, let's say this is chi. One reason why people take 1 in the literature is that so this moduli space is just nice. This is now the fine moduli space. This is because this vector is primitive in the cohomology class. This because the last factor is just 1. So stable equals semistable, and also there is a universal family, so that for example, we can construct virtual fundamental class or so on, universal family. But we can also define Gopakumar-Vafa theory from this moduli space. So although this is not a nice space, but still we can consider, like, we can treat it as a moduli stack, and we can define the Gopakumar-Vafa invariants from this one. The conjecture is that the resulting invariants should be independent of this choice of chi. So this is one of the mystery of this Gopakumar-Vafa story. This is called chi independence phenomena. But I think I will maybe talk data, but so there are some chi independence phenomena. So conventionally, in defining Gopakumar-Vafa invariant, we take chi equal 1, but the resulting invariant should be independent of this choice.
Okay, great. Thank you. Very clear.
So yes, we have also the tangent, the notion of the tangent space. So at each point we have this tangent space. This is identified with the x1. So this is explained that yes, the tangent space corresponds to the first order deformation of the original sheaf E. So then if we given this sheaf, we have this extension that is the correspondence between the tangent and x1. And there is so-called deformation obstruction theory that if the moduli space is singular, then there is some obstruction of extending a sheaf to a sheaf which is of a higher order. So more generally, if you consider some extension of the Artinian link, local Artinian link, so then there is some corresponding class. This is called obstruction class. So that this obstruction class vanishes if and only if the sheaf E can be further extended to some spec of R prime. For example, the R prime might be like Ct over T cube to Ct over T square. So then in this case, there are some obstruction class. So, and this obstruction class vanishes if and only if it can be extended to higher order. So this kind of phenomena can be packaged into the so-called deformation obstruction theory. Sorry, yeah, maybe I skipped some of the part of it, and I just say that this deformation obstruction theory nothing implies that the moduli space is just cut out from this x1 by some number of functions on it, at least formally, where the number of the function is given by the x2. So in particular, this x2 is just 0. For example, this is the case when x is a curve. Then in this case, this moduli space is locally look like X1. So this is in fact smooth. And in fact, so it can be shown to be analytic locally that at each point of the moduli space, this moduli space is a closed subspace of some analytic subset given by a fiber of some analytic map. This is called Kranich map. Anyway, the important point is that locally the moduli space is given by some zero locus of some functions whose number of functions is just given by the dimension of x2. So then I will now go to some generality of the moduli stacks. So let's recall that in the case of x is a point, I said that there are some non-trivial automaton of the vector space, and it gives some abstractions of constructing the fine moduli space. So in fact, there is no, in that case, we cannot construct the moduli space which represents the moduli functor. The notion of stack is used to solve this issue. So roughly speaking, stack is something like a pair of X and G, where G is an algebraic group, and X is some scheme on which G acts. Then we have the notion of quotient stack. So this is something similar to the quotient space of X by G, but it also keeps track of the information of how G acts on this space X. So let's recall that the scheme is regarded as a functor from the category of opposite category of schemes to set. This was given by sending y to yx. So this was just a Yoneda embedding. So in this way, we consider the moduli space as a functor from here to here. But another idea of the stack is replacing the target with the two categories of groupoid. This is because the issue was that the issue was the presence of some automatisms. So the idea is replacing set with some data which also has information of the automatisms. And then here the groupoid means that so this is a category such that any morphism is isomorphism. For example, a category with one object, then giving a groupoid with one object is nothing but giving a group. That is, this is also equivalent to giving the Hom spaces, but which has some invertible element at each element. So this is nothing but this is a group. So in some sense, groupoid is something like a generalization of the group. So the important example of stack is given by this quotient stack. Let algebraic group G acts on a scheme X. So then we have the stack in this way. So this is defined by sending a scheme S to the groupoid of this data. So here this is principal G bundle. And this means that we have some G actions on here whose quotient is S. And this map from G to X is G equivalent. And so this is the object of the image of the groupoid over S. There is also the notion of isomorphisms. So these are given by the isomorphism of its principal G bundles, which commute with maps to X. That is, we have this isomorphism to X. So when x is a point, so then g acts on this point trivially, of course. So in this case, so this is written in this way. So this is the so-called classifying stack. So then there are several notions of stacks. Morphism of stacks is called representable if for any scheme y and y to y, if we take its fiber product, so then this is a scheme. So this is a notion, this is the definition of the representable morphism. So this is known that it is representable if and only if the induced map on orthogonal groups is in fact injective. For example, if we consider just the structure map from BG to point, then of course this is not representable because BG is not a scheme. But for example, if we consider X over G to Y over G, where X and Y are schemes, and G acts on here equivalent, and X to Y is G equivalent, then this is representable. And then a representable morphism is, so this is, sorry, I should say this is called to have the property something. For example, we can say F is a proper morphisms, separated morphisms, finite type morphisms, smooth morphism, or so on for morphism between stacks. If for any scheme Y to Y, then its pullback has this property. So yes, so this one makes sense because of the definition of the representable morphism, so that this is again scheme, and this is a now map between schemes. So the notion of like proper separated or so on makes sense for this morphism. So then we have the nice kinds of stacks called RT stacks. By definition, a stack is an RT stack if the diagonal map is representable, quasi-compact, and separated. So roughly speaking, this means that the fiber of this map is like the automated group of X. That is, the image of this map lies in, of course, the diagonal. So if you take a point of X and X, then the fiber of this map is like the automated group of X. So roughly speaking, this says that the automated group is like quasi-compact and separated. That is not very nice algebraic group. And also there is a scheme T, and yes, are there questions? So there is the scheme T and a smooth surjective morphism H2 to X. So we say that such a scheme is called Atlas. For example, if in the case of quotient stack, then we can take a map from X to here, and this is smooth. And X is a scheme. So this is, in fact, Atlas. And we say that this stack is called the manifold stack if this map can be taken to be étale. This map H is taken to be étale. For example, in this case, in the quotient stack case, if G is a finite group, then the map from X to this quotient stack is in fact étale. But if G is not a finite group, for example, like G for G wave N, then this map is not étale. But nevertheless, sometimes if the automated group of such stabilized group of this action is finite group, then in such a case, it is in fact to manifold stack. We also have the notions of coherent sheaves on empty stacks. So for outing stack, there is notion of coherent sheaves, which consists of a compatible system of coherent sheaves, where we consider some smooth topology on the stack, and the giving a coherent sheaf on X is given by the data of coherent sheaves at each smooth map from a scheme T and satisfying some compatibility conditions. So for example, in the case of quotient stack case, then giving a coherent sheaf on this stack is equivalent to giving a G equivalent coherent sheaf on X. So this is a pair of coherent sheaf on X, and also this by G. So this is isomorphism between G apostrophe F to F, satisfying the cycle condition. So in particular, the coherent sheaves on this classifying stack is equivalent to the category of finite dimensional G representations, because in this case, X is just a point, so F is nothing but the finite dimensional vector space. And giving such a phi G is in fact equivalent to giving G to GLV. So V is for point, which is vector space. So this is nothing but the G representations. So in this way, the considering coherent sheaves on stack is so this has also to do with the representation theory. So then we can consider moduli stacks of coherent sheaves. That is, for a projective scheme X over perfect number field, let's consider the stack that sending S to the groupoid of E, that is a flat family of sheaves over S. So yeah, so now this is now outing stack locally of finite type. So if this is not the target is not a groupoid but a set, then this was not represented by a scheme. But by replacing set with groupoid, then it is realized by a very nice outing stack. And in fact, there are open substacks of finite type corresponding to H stable sheaves and H semistable sheaves. And the point of considering semistability is that this is not of a finite type. Because of the unboundedness issue. Even if I fix some chunk character, this is not of a finite type, as I saw in the case of P1. But if we consider only semi-stable sheaves, then this is open, and this is finite type. Then stable one is also of finite type. So if we consider semi-stable one, then it is much better than the original MV, and stable one, that is still better. But let me give some examples. So suppose that X is just a point, and take V of R in Z. Then the moduli stack of this numerical class is this is nothing but the BGF of C. So so this is because giving a map from here to BGF of C. So this is nothing but giving a GF of principal bundle, J bundle, but giving a principal J bundle is equivalent to giving a rank vector bundle on S. So in this way, so this is we have this isomorphism. So this is possible because we consider the functor where the target is groupoid. If the target is just a category of set, we don't have such a description. And similarly, so this means that we can resolve the issue of the automatism by considering stack. And still we have the issue of the unboundedness in the case of, even in the case of x equal p1, and also with this Chan character. And as I mentioned before, the stack consists of these kinds of ranked vector bundles. But here there are automoism of these vector bundles. So this automoism group is given in this way. And this group is reductive if and only if A equals 0. And for G equal A equals 0, then this is just GL2C. And we have this chain of open emergence. So this is the infinite chain of open emergence of this stack. And because this is the infinite chain of open emergence, this is not of finite type. But this means that we have some stratification of this M20 where each strata corresponds to this point. And this one corresponds to the stratification of this modular space in terms of the Harder-Nashman filtrations. In fact, because we have the Harder-Nashman filtration where OA to FA to O minus A. So this is the Harder-Nashman filtration of FA. And this gives a stratification of each vector bundle in terms of Harder-Nashman filtrations. So, but sometimes we can approximate stack with some schemes. So this is also a very important notion. That is, suppose that the reductive algebraic group G acts on affine scheme, spec R. For finitely generated C algebra R. So then in this case, it is also well known that the invariant ring is also finitely generated C algebra. So then this inclusion induces a map of the spectrum. So this is something similar to the quotient map. In fact, this map induces a map from this stack to the spectrum of the invariant ring. In some sense, this scheme approximates the quotient stack. In the following way. So let's consider the following example. So let's this one-dimensional torus acts on C2 in this way. So this is acts on weight 1 and -1. Then it is easy to see that the invariant ring is generated by only one monomial CXY. And this map forms its over C star to spectrum of the invariant ring. The spectrum of the invariant ring is just one-dimensional affine line, and this map is just given by sending xy to xy. So in fact, this map is equivariant and invariant under this action. And the previous map is given this way. So in this case, the quotient is the dimension of the stack is one-dimensional, and the spectrum of the invariant ring is also one-dimensional. So this looks like the similar to the quotient space. This one. However, we have also similar example, but now the weight is just 1, 1. So then every polynomial of xy has non-negative C-star weight. So the only C-star invariant polynomial is just a constant. So this means that this quotient map is just C over C-star to point. In general, the spectrum of the invariant ring parameterizes not the orbit, but the so-called orbit closures. For example, in the first example, the orbit are like this one. For example, if xy equal a, where a is non-zero, so this is one of the orbit. But there are other orbit like this. Also, there are orbit like this, and the other orbit is just the origin. So that is the locus where x equals 0 and y is non-zero. So this is one of the orbit. So this is space is y equals 0 and x is non-zero. And x equals 0, y is non-zero, this is also one of the orbit. And x equals y equals 0 this is also orbit. But if we consider these three orbit, then if you take its closure, then intersect. So in this way, this space parameterizes orbit closure, where the origin corresponds to this equivalence classes orbit, where the equivalence is given by identifying the orbit whose closures intersect. In a similar way, if we consider this action, then every orbit must have intersection with the origin after taking a closure. So in this way, every orbit is equivalent. So there is on the spectrum of this invariant ring is just 1 point. So there is some generalization of this phenomena due to alpha. So this is a generalization of the map from the quotient stack to the spectrum of the invariant ring. For outing stack X, it is defined, its good moduli space is a scheme X with a morphism such that the pi lower star the factor from Q of X to Q of X by taking its push forward. It's an exact factor. And also the pi lower star of the structure sheaf of this stack is isomorphic to the structure sheaf of the downstairs. For example, this map from spec R over G to spec of the invariant ring. So this is in fact an example of good moduli space. This is because the this push forward factor is nothing but taking the just global section and also taking the G invariant part. But because G is assumed to be reductive, taking G invariant part is in fact exact. And also taking gamma invariant part is also exact because spec R is affine. So this is in fact exact factor. And this one is also biased because the from the definition of pi faster of the stack, this is nothing but the OX is nothing but like R, and the pi upper star is nothing but taking the G invariant. So this is nothing but the structure sheaf from the downstairs. So in this way, so it gives some generalization of this map. So then we can formulate the existence of a nice moduli space for semi-stable sheaves and stable sheaves using the notion of good moduli spaces. So essentially, so this was a classical result, but this is reformulating using the notion of good moduli spaces. So yeah, let's say X is a smooth projectivity. Smoothness is not important. So let's say X is like projective scheme. And H is ample divisor, and take V to be element of H star XQ. So then let's recall that the moduli stacks, we have the moduli stacks of semi-stable sheaves and stable sheaves, which are open substacks of all the moduli stack of coherent sheaves. So then this moduli stack, so this one does not admit good moduli space. But if we consider the open substack of semi-stable sheaves and also stable sheaves, then they admit good moduli spaces. In fact, this is a result of the so-called GIT quotient. So in the case of moduli space of semi-stable sheaves, there is a way to construct moduli spaces as explicit GIT quotient. And in this case, by taking the honest GIT quotient. So this is a GIT quotient stack, and this is a honest GIT quotient. And this is gives a good moduli space in the sense of the previous slide. And in fact, from the main result of GIT, this is in fact a projective scheme. And the stable part is open subscheme. So this is projective and this is open. So in fact, in general, this is a precise projective scheme. And moreover, each point of this good moduli space corresponds to so-called polystable sheaf. That is a direct sum of stable sheaf, so that we have this equality of the reduced Hilbert polynomial. And this map of sending good moduli of a point of the good moduli space, sending a point of the moduli stack to the good moduli space, is given by taking the associated gradient of the Jordan-Heyduck iteration. That is, for each point of this moduli stack, we have the so-called Jordan-Heyduck iterations. As I said, this Jordan-Heyduck iteration itself is not unique, but nevertheless, its associated gradient is unique. So this map is just nothing but the uniquely determined associated gradient of the Jordan-Heyduck iterations. The fact that the Jordan-Heyduck iteration is not unique is that there are some non-trivial fibers of this map. So then let's compare the previous good moduli space with the fine moduli space. Let's recall that if we have some primitivity condition of the chunk characters, for example, like this condition, then this there is some moduli space which represents the usual functor. So this is a functor from the category of schemes to the category of sets. And under this condition, this functor is representable by this moduli space. So in this case, we have the phonic relationship with the good moduli space of and moduli stacks of semi-stable sheaves. So the good point of this condition is that there is no strictly semi-stable sheaves. That is, every semi-stable sheaf is in fact a stable sheaf. So that is, this condition is satisfied. So in general, so we have the open immersion. But under this condition, this open immersion is in fact equality. And also we have this good moduli space. But in the case of moduli space of stable sheaves, there is no non-trivial Jordan-Heyduck iterations. So this map is almost identity or almost isomorphic. But the only difference is that because this is a stack, we have the information of the automatism groups. So even if for stable sheaves, there are some automatism groups, that is C star. So for stable sheaf, the automatism group is just one-dimensional torus. So yes, in the first part of this lecture, I said that in defining this moduli functor, I explained that this is a family of sheaves after taking the equivalence class of divisions. That is, so this is taking the equivalence class of divisions, where the equivalence division is given by taking pullback of line bundles over the base. So this one corresponds to like rigidifying the automatism groups. So that is here on this moduli problem, I don't take this equivalence relation. Here, I take this equivalence relation. So the difference is given by, in fact, so-called C star job. That is, at each point of this moduli stack, we have the automated group. And at each point of this map, the fiber is nothing but BC star. And in general, so this map is, in fact, étale trivial C star job. But this condition implies that there is a universal family. So this implies that there is a map from this moduli space to here, which gives a section of this C star job, which makes this job to be trivial. So job means that so this is a étale locally isomorphic to PC map to MHV. In general, so this is étale locally, but the existence of the universal sheaf implies that this is globally trivial. And in general, so this job is classified by the Clark class. That is also important part of the moduli theory. But if in this condition is satisfied, we don't have such a contribution of the Clark class. And we have the very nice moduli theory. So for example, in the first part of this lecture, I considered this M beta 1. M beta, so this is where the chunk character is 0 beta 1. So in this case, this condition is satisfied as the moduli space is in fact fine. So we have a very nice property of this moduli space. Okay, so there are also non-fine examples. So this is again where X is a point. Then of course this moduli stack of semi-stable sheaves. In the case of X is the point, every sheaf is semi-stable, so we don't have to consider stability condition. But anyway, in this case, the moduli stack is BGFR. And of course, this is not a fine moduli space, but a good moduli space is, so this is a spectrum of the invariant ring of this CGFR, but of course, this is a trivial action, we can just ignore it. And similarly, let's take X to be a smooth projective curve and take the chunk character to be just 0 and n. And of course, this is not a primitive vector. So the previous condition, the previous GCD condition is not satisfied. And the moduli theory is not fine. In fact, this moduli stack consists of zero-dimensional sheaves on X, such that whose Euler characteristic equals to n. So in this case, the Jordan-Haider filtration is that we take the filtration whose subquotient is just the skyscraper sheaf of point on X. So if you take its associated graded, then it corresponds to just giving a zero cycle on X. So its good moduli space is nothing but the symmetric product of X, which sends each zero-dimensional sheaf to its support together with some multiplicity. So in general, for arbitrary stack, it does not admit a good moduli space. But if it admits a good moduli space, it gives quite strong local information of this moduli stack. So this is the approximation by quotient stack, and this is a kind of lunar étale slice theorem for outing stacks. So this is a quite remarkable result by Alpha, Hall, and Gibbs. And the statement is that if X is an Italian outing stack over C, and pi is a good moduli space with a fine diagonal, then for each closed point, there is a fine scheme with an action of reductive group and also Cartesian square. So each vertical maps are étale. And this is Cartesian. So this means that if the routine stack is admits a good moduli space. So it is etabled locally on the good moduli space, isomorphic to such quotient stack, where the action is given by some deductive algebraic group. So this is quite strong and useful result that if we know that the stack is a quotient stack, then we can analyze this stack using representation theory of this group G. So in general, there are many stacks where X is not given by quotient stack. But if we know that it is given locally by quotient stack, then in many points, in many situations, we can reduce the question to this case. So in this way, this is a very strong result. Yeah, so far I considered only the moduli space of Sheaves, but so this is just a reminder about the other moduli theories, like moduli stack of curves, not sheaves. So this is usually used in defining global fitness theory. So this is similar to before we consider some family, but so far I have considered some ambient space X, but in considering moduli stack of curves, we don't fix such ambient space and just consider some flat family of curves. And it is in fact smooth and with morpho stack when the genus is bigger than or equal to 2, because the automatism group of sheets, so this is a non-to-be finite group. However, so this family of curves is not proper because the curve may degenerate to some singular curve. And we need to allow stable curves for compactifying the moduli stack of curves. So there is also definition of stable maps. Well, given variety X, we consider the pair of C and F. So here I also fix some ambient space, but I don't assume that this map is embedding. So if this is embedding, so I could also consider ideal sheaf and again consider also the moduli space of sheaves. But in considering global fitness theory, we consider not a sheaves but a map. So this map is not necessarily embedding. So now she is, but the constraint is that she is almost smooth curve. Well, she is maybe singular, but with some nodal singularities like this. In the case of moduli space by ideal sheaves, there is no constraint on the singularities. So there might be some sort of singularity like this, or even it may be some non-reduced curves. But in the case, in considering stable map, we assume that the curve has at least nodal singularities. And the stability condition is that this F is a morphism such that the automatism group of this map is has only, this is only finite group. For example, if X is a point, and if she is if she is a smooth curve with genus bigger than or equal to 2, then this is automatically stable map. And also, for example, if she is a smooth curve of arbitrary genus, but the map F is just embedding, then this is again a stable map. So the stability happens if there are some like genus 0 curve or genus 1 curve which are mapped to a point by this map F. So this is also the fundamental fact that if we consider the modular stack of stable maps, but here the parameter is that the curve class beta and also the genus of G. So then this is represented by Duini-manifold stack, whose good moduli space. Well, in the case of Duini-manifold stack, good moduli space is also called coarse moduli space. So this is in fact proper moduli space. And this one is used to define the global fit invariant. So this is another part in enigmatic geometry. So now we have the two notions of moduli space of curves, that is like ideal sheaves and or also the moduli space of stable maps. So in fact, these moduli spaces are in fact different. For example, consider X equal P2, and also consider family of curves inside PP2, given in this way. So this is parameterized by some complex number T, and if this is non-zero, then this is a non-singular conic inside PP2. So this is isomorphic to PP1. So let's consider the limit of this curve for T to 0. So if we just naively substitute T equals 0, then we get this equation. So this is y square equals 0 inside P. So this is non-reduced curve inside P2. So this gives the structure sheaf gives a limit of this structure sheaf as a stable sheaf. So I think I should say that. So in this example, I consider not ideal sheaf, but the structure sheaf as a stable sheaf. It is not necessary to that the structure sheaf is stable, but in this example, the structure sheaf is in fact stable. And if we take its limit, then this gives a limit of this gives a limit of the stable sheaf. But we can also consider the limit as a stable map. That is, we have this map ft p1 to p2, which takes uv to u square tuv v square. So when t is non-zero, this is embedding to this non-singular conic. But when t equals 0, this is a 2-to-1 covering over P1. So this is in fact y equals 0. So in particular, so there is automorphism at this point. That is the covering map of this 2-to-1 covering. That is mu2. So in this way, if we consider moduli space of stable sheaves, the moduli space of stable sheaves is always stack, or if we take its good moduli space, this is a scheme. But so that is the automated group of stable sheaf is always C star. If we remove this C star automatism, then it is always a scheme. But for stable map, so there might be some finite group automatisms. So in this example, for T to 0 limit, we have this mu2 automatism at the boundary point. But on this limit, there is no non-trivial automatisms. So in this way, the moduli spaces are defined. So now, finally, today I will also give some comment about the moduli space of object in the derived category. So this is also important in considering the Donaldson-Thomas theory and its Ball crossing. And this gives some formula which expresses dt or pt invariant in terms of some genus 0 Gopakumar-Vafa invariant. So let's consider, so far I have considered moduli space of coherent sheaves. But instead, let's consider moduli space of object in derived category. So let's recall that for projective scheme X, the derived category of coherent sheaves is, so this is a category whose objects consist of these bounded complexes. It is natural and important to consider moduli spaces of objects in derived categories. But there are several issues of considering such moduli spaces. So, in fact, it cannot be presented by a reasonable stack. This is because, so if we, in considering a stack, so the stack theory is used to consider moduli theory where we have just automatisms. But in the case of modular space of object in derived category, the automatism also has some automatisms. So this is because the automatism group has tangent space by form of FF. But the automatism groups of object in derived category also form the stack. This is because the automatism group have automatism given by form -1 FF. So if you only consider coherent sheaf, of course this is 0 if F is coherent sheaf. But if F is object in derived category, then this may not be non-zero. And in this case, we should also consider automatism group as a stack. And similarly, the automatism group of automatism group also has automatism group, or so on. So in general, such a phenomena is formulated in terms of higher outing stack. So vigorously speaking, such a modular theory is constructed by Toen and Baku. So in fact, this is realized as the derived infinity stack. But in the application of enumerative geometry, we don't have to consider such a very big higher stack. And in fact, it is enough to consider object in derived category satisfying the vanishing of the X conditions. So this condition means that there are no higher automatism groups. So in this case, we can consider the usual modular stack, modular functor from the category of scheme to the category of groupoids. And similarly to the case of coherent sheaves, it can be shown to be outing stack that is locally of finite type. So that was a result by Leibniz, but more than 20 years ago. So the condition, so this condition is realized if F lies in a heart of this structure. Of course, F is a coherent sheaf, then this condition is automatically satisfied. And in the previous lecture, I explained about the notion of T structure. And if the object lies in some heart of T structure, then this condition is automatically satisfied. So then we can consider the modular space of objects in a given heart of T structure. However, we also further need some notion of stability condition on the derived category. So this notion of stability condition was introduced by Bridgeland. So in order to formulate some idea from the string theory about Douglas pi stability condition. So in this lecture, so I don't talk so much about the regional stability condition. So I just roughly explain about it. So for a triangulated category, stability condition is a pair of Z and A. So Z is a group homomorphism from the K group of D to the complex numbers, and A is some heart of T structure satisfying some conditions called the positivity property and also has a natural property. So roughly speaking, this Z corresponds to a choice of the slope function. And A is some choice of like a coherent sheaves or something similar to that. So the axiom of stability condition is that there is a positivity property that is for any non-zero object in the heart, we have this condition. So this condition is that the image of the map Z. So this map Z is called the central charge. And the image of this central charge lives in here. In particular, the argument of ZE is very defined from 0 to pi. And similarly to the case of stability condition for curves, we can define the semistable sheaves by using the inequality of the slopes, like this, or like the argument of ZE. And the hard natural properties, so this is just the same property which hold in the case of curves and or even in the higher dimensional case. We have several various examples where C is a smooth projective curve, then the pair of Z and C, Z is of this kind of central charge, and Kavli. So this is a standard heart. This is gives the example of stability conditions. And also for Arabian category A, and let's assume that A has only finite number of simple objects which generates this category A. So this means that A is extension closure of this simple object S1 to Sk. So here I write it. So this is extension closure. That every object in this Arabian category has some filtration whose associated grade is just a direct sum of this Si. So then in this case, because every object in A has some filtrations, whose subquotient is 1 of SSI, then by just taking the image of the central charge, just by taking the image of each simple object by the central charge, then we can just construct a stability condition. Like, for example, if there are only two simple objects, we can consider like ZS1 and ZS2, so on. So this happens when A is like the module category over some finite dimensional algebras, or like representation of some cleavers. So then the important point is that Bridgeland proved that the set of stability conditions on a given triangulated category D, so this satisfying some more reasonable conditions, which I don't explain too much, but they are so-called support property, numerical property, so it forms a complex manifold. And we write stub X to be the space for stability conditions for when D is derived category of coherent sheaves. So this is a very important notion, and a very interesting and important research subject in mirror symmetry, irrational geometry, and other related areas. And of course, this is also important in enumerative geometry. However, there are some issues about this service, so it is extremely difficult to construct example of stability conditions in higher dimensional varieties. So there are some classical notions like these stability conditions using the ample line bundles, which I mentioned. But so this classical stability condition does not fit into Bridgeland's sense of stability conditions when the dimension of X is bigger than or equal to 2. So in general, it is expected that there are some stability conditions on derived category of this form. So this is not important. For given choice of p plus I omega, so this is I is square root of -1. So this is where the imaginary part is ample class. So this one lies in the complexified ample form. And the central charge should be maybe given this way. Well, probably there might be some correction term coming from the quantum correction. But in general, for arbitrary C4, we expect that there is a stability condition of this form. And so the existence of such stability condition is known when the dimension of X is less than or equal to 2. But in the one-dimensional case, this is nothing but the one, essentially the one which was mentioned, that we have like cof of C, theta and cof of C, given by minus degree plus I and line rank. But the point is that in the higher dimensional case, there is no stability condition where the corresponding heart is the standard one. We have to construct some other heart of T structure which is different from the standard one. In the two-dimensional case, using the classical Bogomo-Jizuka inequality, so there is a inequality of the Chan characters for semistable sheaves. So this is called Bogomo-Jizuka inequality in the case of surfaces. And using this inequality, it was proven by Alka and Latam, but originally the idea is coming from the Bridgeland's construction of the stability conditions on KC surfaces. But anyway, so in the surface case, we can construct such stability conditions. But in the three-dimensional case, so this construction is non-trivial, and in my paper with Bayer and McCreary, we reduced this type of construction to showing BG type inequality, but evaluating the third chunk character for some complexes. So that are called tilt stable object, and this is called PMT inequality conjecture. So the construction in the Seaford case is maybe a bit technical, and this is not main subject of this lecture, so I just briefly explain. So for each smooth projective Seaford and for each element, we first consider some sort of pair of subcategories, which form the torsion pair. That is something similarly to the notion of torsion sheaves and torsion free sheaves. And in the previous lecture, I explained that using the torsion sheaves and torsion free sheaves, we can construct other heart of T structure using that is when T is the torsion sheaves and F is the torsion free sheave. So there is some heart of T structure A such that the -1 cohomology lives in F and H0 lives in T. And this notion can be more generalized to so-called torsion pair. That is, so this one is it gives the example of such a torsion pair. And using this torsion pair, we can define as a heart of T structure. So this is the called tilting of the category of coherent sheaves. So then the property of this first tilting heart is that so yes, so this V1B is so this is nothing but the first chunk character twisted by the B field. Anyway, so you can regard it as like a first chunk character. And this is the imaginary part of the central charge. So eventually I want to construct some heart of T structure where the imaginary part of the central charge is bigger than or equal to 0. And if the imaginary part is 0, then the real part must be negative. So this is the pair. This is the heart of T structure I want to construct. So the point of this construction is that after tilting, we have these conditions. Either this vector is positive, or this one is 0 and the imaginary part is positive, or this 0 but this one is negative, it's positive. So this means that this three vector looks like something similar to the rank first chunk class and second chunk class on surfaces. So this is the similar condition. So from this observation, we defined this kind of slope function on the first tilting category, and tried to do something similar operations. But in order to apply it, we need some conjecture inequality of the third chunk character. So this is the proposed inequality. And in fact, in our papers, our condition is that if nu equals 0, then V3B is less than or equal to 1 over 8 V1B. But later, in Bayer-Macris theory papers, they showed that this conjecture is equivalent to this inequality without nu equals 0 condition. So if this inequality holds, then using similar operation, we showed that we have in fact stability condition of this form. So this is anyway. So the important point is that this conjecture is important. That is, in fact, assuming this conjecture will also have several important results in birational geometry and also like Castel-Nuovo type inequality for curves or so on. And it also has applications to animative geometry. So this conjecture is open in many cases of threefold, but it is proven, for example, like Arbian threefold, Fano threefold, Quintic threefolds, and some other Calabian threefolds. But this is not known for like general type threefold case. Anyway, so the conclusion of this lecture is that we also have the modular space of the semistable object in derived category. that is using the notion of Breach-channel stability conditions and also this BMT inequality conjecture. That if X is two-dimensional or three-dimensional, satisfying this inequality conjecture. And if we consider stability condition which lies in the connected component of this particular choice of stability conditions, then we have a nice modular stack of semi-stable object. So in fact, this is a outing stack of finite type, and it also admits a good modular space. So contrary to the case of semi-stable sheaves, we don't know whether this is projective or not. So in the case of semi-stable sheaf, this modular stack can be constructed as an explicit generative quotient stack. And this is known to be a projective scheme. But in this case, it is not known whether this is a projective scheme. We only know that abstractly this is a proper algebraic space. Anyway, so this is enough for the application to the enumerative geometry. So today I stop here, and in the next lecture I will talk about Donaldson autonomous theory using the modular space which I discussed today. So yes, thank you very much.